Okay, we'll have a quick, brief lecture on lipids and what lipids are. So if you're reading along, we'll just briefly introduce what lipids are and talk about waxes, triglycerides, a little bit about the reactions of triglycerides, which we've seen before, phospholipids, steroids, and prostaglandins, and not really touch on terpenes. So the main point of this is to just give you an introduction into what lipids are. They're actually different than the other biomolecules that we've talked about in that they don't have common structural features. They actually just are defined by their partition into nonpolar solvents. So they're defined by solubility in a nonpolar solvent, a physical property, rather than by a chemical structure. So if you took a human and blended them up and went to extract them between water and gasoline, lipids would be those things that you would find in the gasoline layer. So these are going to be mainly hydrocarbons with a few functional groups. You'll see some similarities, such as between a wax and a triacylglycerol, that they both have esters, but that is not a necessity to be a lipid. What you'll really notice is that they just have lots of hydrocarbon motifs. So just lots of carbons and hydrogens in them. So lipids, again, categorized by their physical properties rather than chemical structure. So again, these are molecules that you'd extract into a non-polar solvent. So they include fats and oils and waxes, vitamins, hormones, a bunch of different molecules. So they're defined into a couple different classifications, those complex lipids. They're complex because they can actually be hydrolyzed into smaller individual portions. So such as waxed triglycerides and phospholipids. So these are things that tend to contain esters. And then you have simple lipids that can't be hydrolyzed. And simple is not due to their structure, because I wouldn't consider vitamin A simple or cortisone simple or PGE1 simple. But these don't hydrolyze in acidic or basic conditions. So they would be considered a simple lipid, where this one here that just has normal alkane chains, looking kind of simple, but yet actually has an ester that can be hydrolyzed. That is referred to as a complex lipid. So complex lipids can be broken into smaller parts by hydrolysis. So like I mentioned, some of them have common groups, such as waxes and triacylglycerols and phospholipids. They all contain a ester. And then we'll have the, this shouldn't be complex. They have complex structures, but they're referred to as simple lipids. So let's erase that. Okay, so let's start off with fatty acids. They tend to be classified by their size and whether they have even versus odd number in there. So natural fatty acids tend to be unbranched, so they're just straight hydrocarbon chains, and they tend to have an even number of carbons. Then we classify them based on their melting points. Fats are those that are solid at room temperature, and oils are those that are liquid at room temperature. And then by the saturation level. What we mean by saturation level is if they have as many hydrogens and carbons as possible, meaning all sp3 CH bonds, then we would refer to that as a saturated fatty acid. If it has a double bond, then they tend to be in the cis configuration, and these are referred to as unsaturated, meaning that we could actually add more hydrogens to them. What's interesting is the melting points over here. So for this saturated fatty acid, it has a melting point of 69. When we introduce one double bond in there, it actually drops the melting point dramatically down to 13. And again, those double bonds tend to be cis. If we have two double bonds in there, now we're actually a liquid below 0 degrees Celsius. So when it's freezing, these would still be a liquid. And if you have multiple double bonds, you can even drop the melting point further. And so the reason for this is if you are a straight chain alkane, you tend to pack together very well, like pencils. You have lots of surface area contact, and so you can have lots of intermolecular interactions, van der Waals forces, or London dispersion forces that tend to stabilize those intermolecular interactions. And so you have a higher melting point to get those molecules to slide past each other in the liquid phase. Once you start putting the kink in there, you now have a shape, and so those molecules are going to have a harder time packing together. They'll have less surface area to interact with, and so I view those as somewhat spherical, where they have small contact on the surface with another molecule. So not much intermolecular interaction, and so the melting point tends to be a lot lower. So we can look at some saturated fatty acids. I've got a picture of Pringles over here. Another way to look at them is they just are able to snuggle up with each other very efficiently and have a lot of these London dispersion forces. And so you can see as we increase the chain length, we go from 12 to 14, the melting point goes up, and we go to 16, the melting point just steadily increases because we get more and more of these London dispersion forces. So for straight chain fatty acids, the melting point increases as we increase the chain length. Again, because they can pack together very efficiently. If we include a double bond in there, you notice that the melting point actually drops. So even though we have a different number of carbons over here, it really is a function of the number of double bonds. If we have the same number of double bonds, of course, those with more carbons will have a higher melting point because, again, this tail here being longer will allow a little bit more interaction with other molecules. But if we throw in another double bond for the same number of carbons, we see the melting point drop. If we throw in a third double bond, we see it drop again. And in this case here, even though we've increased the chain length, we've increased the number of double bonds, and those drop. And so we get molecules that actually exist in the liquid state clear down to -50. So even in the coldest of winters, these would remain in the liquid state. Okay, so we really don't find a lot of free fatty acids biologically. We tend to store them as triacylglycerols that we'll talk about in just a second. So we tend to find them stored in ester forms. We do have free fatty acids. That's actually how we metabolize them. We just don't have a lot of them floating around, or hopefully you don't have a lot. So let's talk about our first real biological lipid, and that is waxes. And so waxes are an ester of a very long chain alcohol. In fact, this example here actually has 30 carbons. And then it is involved in an ester bond with a saturated fatty acid that is 16 carbons long. So we have this molecule drawn out on the bottom, and you can see that that is a very large molecule with lots of places to interact and experience London dispersion forces. So these have very high melting points. And so waxes that we use in candles tend to have very high melting points, and you can in fact get to such long chains that they don't even really melt. They're more like plastics, so very difficult to melt. And so these are biologically used. Plants use them to coat their leaves to prevent evaporation of water and to protect themselves from insects. And insects actually use wax, best known being bees, that use it to build their honeycomb to store their young and honey in. So again, waxes are a fatty acid, very long chain, and then an even longer chain alcohol. And so we've got a couple examples here. So beeswax, the fatty acid is 16 carbons and the alcohol is 30 carbons. So the source is honeycomb, and it's used as candles and shoe polish and wax, wax paper. Carnauba wax, you may see this for polishing. I believe you can find it in car polish and other waxes. It's got a much longer fatty acid there. So the fatty acid actually has 26 carbons. Then you got jojoba wax, a little bit shorter fatty acid than carnauba wax of 20 carbons, but longer than the beeswax. But the alcohol is also shorter with 20 carbons. So it comes from the jojoba bush, and it's used in candles and soaps and cosmetics. You can see an example of actual beeswax down there. So 16 carbons in the fatty acid and 30 carbons in the alcohol. So those are classified as lipids because if you went to extract, they would go into the nonpolar solvent. So related to waxes are triacylglycerols. Okay, related to waxes are these triacylglycerols. Now, triacylglycerols, like the name says, is they have 3 acyls attached to a glycerol molecule. What glycerol is this trialcohol, so 3 carbons with an OH on each carbon. And if you take fatty acids and you take 3 of them and esterify each alcohol, then you get a triacylglycerol, which is really the proper term for a fat or an oil, again, based on if they are solid or liquid at room temperature. So we can see the full structure of a triacylglycerol below, and you can see that each one of those fatty acids can be different. They don't have to, but they can and quite frequently are different. And you can have mixes and matches of all different types of fatty acids on there. And so this is actually how we store fats in our body as triacylglycerols. And then when we go to metabolism, metabolize them, we actually free the fatty acids and then we break them down and get energy. So as I mentioned before, the proper way to identify a fat or acid are these triacylglycerols. And so again, it depends on their physical state at room temperature. So notice here in this example, this triacylglycerol, we've got a bunch of saturated fatty acids. So that's going to pack together really well, and that is what is considered a fat. And so this is the fat that you find in meat, the white stuff here, or butter, or even Crisco, these very saturated triacylglycerols. Now, oils, on the other hand, tend to have a fatty acid, one or many of them, that tend to have a double bond in them. And again, natural double bonds in fats tend to be of the cis configuration, and those put a kink in this triacylglycerol that allow them to pack together less efficiently, which makes them liquids at room temperature. Here's just an interesting slide of the distribution of polyunsaturated, meaning has many double bonds. Monounsaturated means a single double bond, or saturated means no double bonds in the fatty acids. And so you can see that beef tallow or beef fat has about an equal mix of monosaturated and saturated. Coconut oil, which is actually supposed to be healthy for you, actually has predominantly saturated fats in them. Supposedly, the coconut oil actually has shorter fatty acid chains, somewhere around C14, and it's thought that those short saturated fatty acids are actually healthy for you. But that could change in the future, because typically saturated fatty acids are the ones that, to me, taste better. As you can see in all this stuff, doesn't that look delicious? They all have saturated fatty acids, where those that have unsaturated or double bonds tend to be in stuff like, ugh, yuck, avocados and other stuff that doesn't taste good, but probably is good for you. So the stuff that tastes good, probably not good for you. Stuff that doesn't taste good is probably good for you. One of those questions of humanity. Okay. Now, people have been trying to lose weight for a long time, and they realize that fat contributes to obesity. So one way to ideally reduce obesity is to actually reduce your fat intake. Okay, so one of the ways that people are trying to get it so that you can lose weight is by reducing your fat intake. But fat tastes oh so good. So here's an interesting molecule that combines carbohydrates and fatty acids. So you can see in the green, we've got the sugar, so that's actually sucrose. And then each one of those alcohols is involved in an ester bond, which is a straight chain fatty acid. So it has a similar texture and taste to natural fats. It's known as olestra. It's not broken down in the intestinal tract, since it's not really a natural fat, but it has the same taste. The problem is, if someone sees a fat-free food or one that has fewer calories, they tend to eat more of it. So olestra actually would pass through the intestinal tract unmodified, and it is a very greasy molecule. And so as you can see off to the side, after a while, with people overeating these products, they had to put a warning on there that olestra may cause abdominal cramping and loose stools. I've seen other warnings that actually stated this may lead to explosive diarrhea. The other issue with this is it would actually absorb prevent absorption of the fat-soluble vitamins A, D, E, and K. And so they had to add those additional vitamins in so that you'd actually get some. Anyway, it led to a problem, and so you don't see much of olestra anymore. So in our body, we take these triacylglycerols that are stored in our adipose tissue. So if you look at adipose tissue, you've just got these cells that are just full of fat, almost like if you had a soup that had those little oil droplets at the top. You put some in the fridge and it ended up solidifying. So in our bodies, they're not solid, they tend to be liquid. But what we do is we take the fat, high energy density right here. There's no water. It's all these triacylglycerols. Those of you in nutrition know that you get 9 calories, I believe, per gram of fat, where it's only 4 calories per gram of carbohydrates. So fat is a very energy dense material that we use when we run out of our carbohydrate stores. Oh yeah, there it is right there, 9 kcals. And when we say kcals, that's equal to 9 calories, big C, which are nutritional calories per gram. So a lot of energy stored in fat. So our bodies will use lipases, which are enzymes that break down that ester and again make glycerol, and releases 3 fatty acids that are further metabolized to eventually CO2 and water. So a little bit interesting side note is that yes, fat leads to water. So you may have heard the story about the camel storing water in its hump. And that's not entirely false, because that hump is actually mostly fat. And when you go to metabolize fat, you actually do produce water. And camels have an interesting way to recoup water from their breath in their nostrils. So they do recoup some of the water from hydrolyzing fats found in their hump. So it's not entirely false that camels store some water in their hump. So soap making is a very similar process to what we see above. You actually hydrolyze these triacylglycerols and make free fatty acids. So here is a triacylglycerol. You mix it with a base. This process is called saponification, and you end up with 3 carboxylates and glycerol. And so if you take these carboxylates, they end up having a polar head group and a very nonpolar tail. And these assemble together in these micelles, where the polar head group faces out towards the water. The nonpolar tails surround nonpolar things such as grease and oils, and forms these actually micelles, spherical structures that actually wash the grease and oil and grime away. So you can make soap pretty much out of any fat/oil, and you get a byproduct, glycerol, and soap. Something interesting about glycerol is it actually is used in cosmetics to actually smooth skin. So right now, if you're using a bunch of alcohol hand sanitizer, one of the components that they include is glycerol. So if you just used straight alcohol, it would dry out your skin. So they include some glycerol, and that keeps your hands from drying out. So you can just make soap. This way you end up with glycerol and the soap molecule. Kind of gives you a soft soap, but the glycerol moisturizes your skin. You can also separate out the glycerol and just get the soap, and then you end up getting harder bar type soaps. Anyway, here is just another example of the micelles that you get. So like I mentioned, they're actually 3-dimensional or spherical, and the grease and grime is surrounded by the nonpolar tail, and the polar head groups actually associate with the water and wash the dirt away. So as we talked about, we can classify these into simple and complex or hydrolyzable lipids. And we've got one more lipid lipid to talk about. Now, 2 more lipids to talk about. So these triacylglycerols right here are fats or oils, depending on their physical state or room temperature. But we can replace one of these fatty acids here off of this oxygen with a phosphate group. And we saw this phosphate group back in the nucleic acid chapter. And so this is now referred to as a phospholipid. It's got a polar head group and these nonpolar tails. If you've had biology before, you know that those polar head groups and those nonpolar tails assemble into a bilayer to make a membrane. And so the ionic heads or the charged heads or these phosphate heads point out towards the aqueous. The nonpolar tails associate with each other, making a bileaflet. And that is what protects our cells and separates our cells from each other. Now, if we just had these lipids in there, our cell membranes actually may get pretty stiff. And what we want is a fluid cell membrane that can adapt to mechanical stresses. So when we bump into something, we don't want our cells to break. We want them to be able to flex. So our bodies control the composition of our membranes, and we have just the right mix of saturated fatty acids and unsaturated fatty acids. So the saturated ones tend to decrease membrane fluidity. The unsaturated increase the membrane fluidity. You don't want too many unsaturated because they don't pack together very well, and so you'd end up with a leaky membrane. So you need the right mix. And there is one other molecule that we include in our membranes, and that is cholesterol, and that allows a lot of flexibility. So let's just talk about these really quick. So this structure off to the left there, that is what's referred to as the steroid core. So steroids have this 6-6 offset 6 5-membered ring system. And so they label the rings A, B, C, and D, but all steroids have this common core. And steroids, you may think of just giving you muscles, and they do so much more. So in fact, the most common steroid is actually cholesterol. And so it's found in membranes and incorporate or allows fluidity of the membrane. So it's actually synthesized from this interesting molecule right here, this squalene, a very interesting reaction. It actually kind of just folds up into this structure right there. So there's 8 stereocenters in cholesterol. So there's 256 possible stereoisomers, but only 1 is biologically relevant. So really interesting that we just chose 1 out of 256 for all the uses that cholesterol undergoes. So there are other steroids. There's sex hormones. We refer to them as androgens. For the male hormones, they're synthesized in the testes, and they're responsible for the development of the male sex characteristics, such as a deep voice and hair on your face, and all the other fun changes that men go through puberty. Female sex hormones are referred to as the estrogens. And so when you talk about estrogens, there's actually a class of them. Testosterone is a specific androgen, and estrogens, there's actually 3 main ones: estradiol, estrone, and progesterone. And so it's just kind of interesting to look at the differences in these molecules. So for example, we look at estradiol, female sex hormone, in comparison to 5-alpha dehydrotestosterone, a male androgen. And really the biggest difference is this is not aromatic here and has a CH3. Everything else matches up. So you take away that CH3, aromatize this, which would convert that carbonyl into an alcohol, and all of a sudden you have a female sex hormone. So very similar in structures, but those small differences make a huge biological difference. So again, the male sex hormones are referred to as androgens, and the female sex hormones are referred to as the estrogens. But notice they all have this 6-6 offset 6 5-membered ring system. And then finally, prostaglandins. These are really interesting molecules that come from free fatty acids and are folded up into these molecules here. These tend to be localized hormones. They're formed at the site of action, and they're involved in blood pressure, blood clotting, allergic response, digestive activity, labor onset, inflammation, clotting, fever, pain, sleep-wake cycle. And these are my favorite molecules in the whole world. And I could go on for days, and I won't. So we'll just leave it at that sad point, is prostaglandins. And there's some related molecules such as the thromboxanes and leukotrienes. And these are all interesting because they're derived from arachidonic acid, which is this molecule right here. And your body tends to wrap them up into these really interesting molecules that have all sorts of interesting properties. So these are hormones that we typically don't talk about. When you think of hormones, you think of the steroids and oxytocin and maybe insulin and other things, but these are localized hormones that do very interesting things. So just to close up, prostaglandins, there's a whole family of them, and they classify them as PGAs, Bs, Cs, and Ds, depending on the decoration of the 5-membered ring there. And then they have further classifications as like PGE1 or PGE2, depending on the functional groups on these little tails right here. Well, that's for it for lipids. Just a little survey of what lipids are based on their physical characteristics and some of the different structures that are included in that family. That's it. That is the last of the organic chemistry lectures and the biochemistry section. So if you're listening to this, you have survived.